Well, hello and welcome everybody. Welcome to our summer students in particular. We're very excited to have Zoheyr Doctor visiting us today to give the CITA seminar. Zoheyr is the Sierra Board of Visitors Research Professor at Northwestern University. He obtained his PhD in 2018 from the University of Chicago, worked as a postdoc at the University of Oregon before moving to Northwestern. He's an expert on gravitational waves and a big player in the LIGO scientific collaboration in terms of gravitational wave discoveries and population analyses. And today he's going to be telling us about advances in modeling gravitational wave sources. So Zoheyr, welcome. Please take it away.
Thank you, Phil, and thank you all for having me here. Just a little tidbit about this video you're seeing. This is just a fun little animation I made that represents a bunch of the black holes and neutron stars that we've detected with LIGO and Virgo. And so I'm going to be telling you about these later today, but this is just some eye candy to get things started. So here's the actual title slide for my talk. Let's see, here we go. So thank you, Phil, for the introduction. Yes, I'm coming from Northwestern and Sierra, another institute sort of similar to this, dedicated to astrophysics and astronomy. I'm also a member of the LIGO Virgo Cagra collaboration, and you can also follow me on social media as well if you're interested. So yeah, today I'll be telling you about ways that we are modeling gravitational wave sources and sort of the frontier of this type of work. So let's go back to the beginning of the story. In my title, there was the word gravitation. So we have to start with Einstein. And about a century ago, he discovered the mathematical theory of general relativity. And one of the things that came out from that theory was that there were traveling waves in the space-time metric. And basically, these waves would change the distances between neighboring observers. And so here's a depiction of, let's say you had an entire cylinder of observers and a gravitational wave was passing through this cylinder, how the distances between all those observers would be changing over time. So you can see this sort of undulating effect, but this is hugely magnified, this effect. So in reality, these perturbations, these gravitational waves, they are very, very minuscule. They create fractional changes in distance of order 10 to the minus 20, 10 to the minus 22, something like that. So you need some very advanced detectors to be able to detect these gravitational waves, these like small ripples in space-time. And so we had two of these detectors online in the early 2000s and onwards. These were known as the Laser Interferometer Gravitational Wave Observatory. There was one in Livingston, Louisiana, and one in Hanford, Washington. And you can see these facilities are massive. So there are these two buildings for the two detectors, but there's also these massive long arms. And each of those arms has these lasers that are running down to mirrors on the end that are then, those lasers are projected back. And we're able to use that whole system to detect gravitational waves. Now, I'm not going to go into how the detectors work. We're going to talk about astrophysics and data analysis today, but this is really the sort of state of the art. And there's also two more detectors that are going to be coming online as well. There's Virgo, which is in Europe, that had already done some observations with LIGO before. And there's also the Cagra detector that's going to be turning on for the first time next month. So, so these detectors turned on, they went under some upgrades, and then in 2015, they were turned back on in a sort of advanced mode. And a day or two after turning on the detectors, we saw a signal that looked like this. So this is just showing what's in the Hanford detector. So this was September 14th, 2015, which is actually a long time ago now, I realize, but it feels like yesterday. And over time, we saw this signal, which was increasing in amplitude and in frequency until some sort of catastrophic event where suddenly the signal peters out. And people knew what this type of gravitational wave signal would be the marker of. And it is the marker of two black holes spiraling in on each other and then eventually colliding into one final black hole. So here I've just shown sort of pictorially what's happening to these black holes and how that maps onto this signature that we're actually reading out in the data from our interferometers. Now, we didn't just see that signal in the Hanford detector, we also saw it in the Livingston detector, and you can see that overlaid right here. And there's a beautiful agreement between what both of the detectors were seeing. And that was telling us that this couldn't have been something that was coming from Earth. It was something from space, something common astrophysically that was creating these signals in these detectors. So this was a massive feat. The world was very excited by this, and it led to the Nobel Prize in physics. I didn't win it; it wasn't me, but other people did. So that was really exciting. So that led to people doing all types of investigations of black holes and running expensive simulations. So here I'm showing just one example of one of these expensive simulations from SXS, where they've put it on a background of stars. You can see it's a little choppy because it's going through zoom, but you can see the two black holes spiraling in on each other. And then in a second here, they're going to merge into one final black hole. And that black hole is then going to ring down until it's sort of in a steady state. And so that exact kind of action was then seen in the signal. So all of this was coming together really nicely. And from that one detection, we were able to say that there were two roughly 30 solar mass black holes that had collided to create that signal. They were roughly half a gigaparsec away. That's a redshift of 0.1 for those of you who can think in redshift. And the spin of the larger black hole had to be less than about 0.7. So we couldn't measure the spin of that more massive black hole very well, but we could put some constraints on it. The less massive black hole is even harder to put any constraints on. But this is all to say that we can actually measure the properties of these black holes that collided with each other from those wiggles I showed you in the last slide. So we have a whole infrastructure for doing that, and I'll tell you a little bit about that in a couple moments. So that was the big discovery, but that wasn't just it. That was just the beginning. In 2017, we detected a much longer signal. You can see this is like seconds long compared to the last one, which was just milliseconds long. And so we detected, again, a beautiful increase in frequency and amplitude, and then a sudden cutoff of the signal. And then just a couple of seconds later, in gamma ray instruments, there was a gamma ray burst that was detected. And so this was all telling us that something exciting was happening. So people started pointing optical telescopes and other instruments to see what was going on. I was working with a team through the Dark Energy Survey and some others, and we pointed the dark energy camera in the vicinity of where this gravitational wave signal was coming from, and we saw a nice, beautiful, bright spot next to a galaxy that wasn't there earlier, just a few weeks earlier. And many other teams did the same. So all of this was telling us that what we had observed was two neutron stars colliding. So this was really exciting because not only did it tell us that that neutron stars can actually merge, but they also produce this whole light show of electromagnetic counterparts that we can observe and then use all of these things together to study these very interesting objects and do a lot of other interesting science that's seemingly unconnected. So for example, we did measurements of the Hubble constant by putting together these different data sets. So Maya's been very involved in that kind of work, for example. So this was just an absolutely momentous discovery. I really thought that after the Nobel Prize winning discovery, it couldn't get any better, but this really was, I think, in many ways, the peak. And of course, if you can merge two neutron stars and you can merge two black holes, well, then you'd think you'd be able to merge a black hole and a neutron star. And indeed, the universe did do that during a time that we could actually measure it. And so we were finally able to measure a couple of neutron star black hole mergers. This was in the beginning of 2020. And since then, we've also reported a few more that we have found in our data. So we've kind of filled out the trifecta of these different sources. And putting this all together, there's a really nice illustration from Aaron Geller at Northwestern showing all of the gravitational wave sources that we've detected and overlaid with other black holes and neutron stars we've detected through other means. So up here in blue, you can see individual black hole masses that merged and then what their final mass was. And then down here in orange, we've got the neutron stars. Some of these things, we don't actually know what they were or what they turned into after they merged. So they're sort of shown in a blue and orange. And then on the sides, we've got these black holes that have been detected through electromagnetic means, and then neutron stars detected through electromagnetic means. So this is like the go-to figure if someone asks you, how many black holes have we detected out there in the universe or neutron stars? This is a really nice illustration of all of that. Okay, so that's where we are now. I should mention that here we've got around 90 signals, 90 plus or minus a few, just because of depending on how you threshold what counts as a signal and what not, but that's the number that we're at. And we're about to turn the LIGO, Virgo, and Cogger detectors back on again at the end of this month. So 04 is going to run for probably about 18 months, I think is the plan right now. And then it will turn off again, wait a few years, and then we'll have 05, we'll have even better sensitivity. So right now we're looking at, for the LIGO detectors, around 160 to 190 megaparsecs out that we're going to be able to detect these mergers. So every time we observe, we try to just get a little bit farther out there, and you go out farther in distance, you take the cube of that, and that, because that's you're getting the whole volume, right? So just a little extra sensitivity to get you farther distance is going to get you a lot more in volume. So that's a lot more sources.
Hi,
so
could I just jump in with a quick question from a distance here? In India, LIGO has now been funded. Do you know what the time scale is? It's not going to be ready for 05, presumably, but do you think do you have any idea when it's going to reach fruition to become online?
Yeah, I actually don't know what the latest estimate is of when it will be online, but I'm 99% sure it will not be by 05. It will probably be.
Probably not.
But, I don't know if any of the other LVK people in the room know. Okay.
LIGO plan, how long is LIGO plan to continue to operate?
After 05? That is still in the works, is my understanding. So
as long as they go back to generation.
Yeah, I think it's somewhat funding dependent. So I think that's part of what's happening now, is having those conversations with NSF and
expectation that the other technicals will be operating.
Yeah.
The one caveat to that, Chris, is what we call afterwatch. The one caveat to that is what we call astrowatch, and it's basically if we get galactic supernova, really want to galactic supernova vector on. So it'd be great if we had 4, but we want to have at least 1. So there might be some bridging, planning, and as Zoe mentioned, it's.
Any other questions? Because we're gonna switch gears a little bit now. All right, so yeah, more observations starting very soon. So keep your eyes peeled. At the end of the month, you'll probably see us tweeting from the LIGO account about alerts and things like that. So it should be a very fun period. Okay, one thing I just wanted to make a quick aside about was that making all of this LIGO science happen requires thousands of people, okay, all working together, oftentimes doing a lot of nitty-gritty work. And I just wanted to take a second to highlight a blog we have called Humans of LIGO, where we are highlighting different people across the collaboration. We've got high schoolers all the way to Nobel Prize winners that we have profiled. We just write a short quote. We take a short quote from each of the people about something they're interested in. And so you can see actually Maya was featured back in 2019. And so this is just a nice place to maybe show your students just sort of diversity of scientists that are working on this, and how it's really a team effort to make all this science happen. Okay, quick aside there, but let's go back to these few events, these gravitational wave events that we have detected? What have we learned from them individually? Instead of trying to look at them together in one population, what can we just learn from looking at them individually in their individual parameters? The way that we can do that is using Bayesian inference. So I've written Bayes' rule here on the bottom left. And what this inference scheme enables us to do is we can take some source parameters. So let's say the masses of the two black holes, the spins of the two black holes, their distance away, all of these parameters that describe the gravitational wave source. And we can figure out how likely is the data that we actually observed, given that that was the source. And we can try that for lots of different source parameters. And that enables us to get a whole posterior distribution for each event on what its masses, its spins, properties in general are. So that's how we make all these actual estimates of what these events represent. So here's a few of the tidbits of what we've learned. Firstly, we know that binary black holes, binary neutron stars, and neutron star black holes can actually merge within the age of the universe. So that was the first obvious thing you learned. We've also learned that some merging black holes do spin. So I told you that first event, we couldn't tell whether it was spinning or not, but we have had events where we could say unequivocally that it was spinning. The merging objects can have quite unequal masses. So we have, I think, one event that's around 10-to-1 in the mass ratio of the two merging objects. So that's exciting. And the black holes and the neutron stars that we're detecting from gravitational waves, they seem to have some slightly different properties from those that we've observed electromagnetically. And so this is also a very interesting puzzle that we're trying to untangle. And I'll tell you a little bit about how we're doing that later on. I see there's a question in the chat. I will try to get to it, or Phil can maybe read it out for me.
The question is about LISA and future generation detectors. Maybe let's get back to this at the end.
Yeah, I think that would be great. Let's get back to that. Yeah. Okay. All right, so those were a few cool things we learned, but I didn't tell you about this question, which is how are these mergers even produced in the first place? This is a huge question that we still don't have the answer to. It's the holy grail question. So we know we can detect them, but we don't know how they got there. So naively, you might think, well, what if I just have two stars in a binary? The two stars turn into black holes or neutron stars, and then they emit gravitational waves and they collide. So I start with my two stars, turn into black holes, and I try to merge them through gravitational waves into one final black hole. It turns out this does not work. Okay, why? Well, we can ask ourselves, how far do I have to make these black holes apart from each other, or neutron stars, whatever they are? How far do they have to be apart for them to be able to merge within one Hubble time? So we can do that calculation. So here I've just written the equation for how to get the separation as a function of the merger time and the mass. So if we plug in, let's say 60 solar masses, just like the two black holes we had detected originally, one Hubble time, and then we find that the two objects had to have been about 50 solar radii apart. So what that's telling us is that for these two objects to actually merge within a Hubble time, they must have been closer than the radii of the stars that would have created them. So if there were two stars, those two stars would have expanded to such large sizes, they would have already essentially enveloped each other and turned into one object before they ever had a chance to turn into two black holes or neutron stars that could collide. So something else is going on here than this really simplistic story that I showed before. So how can we solve this big mystery? And as you can imagine, the theorists have gone at it with many, many different ideas. Okay, so one possibility might be that the compact objects are somehow in some dynamical environment. They're all in a very dense environment and they're able to interact often. And because of those interactions, sometimes they're able to actually get close enough they can merge within a Hubble time. So this is something that Claire, for example, has been working on. Another possibility is that maybe the two stars are in binaries, but there's there's some sort of binary interactions between the two stars or the star and the compact object as they're evolving that somehow bring the two compact objects close enough that they can merge. Or maybe they're in some very weird environment, like in an AGN disk or something, where there are all these other interactions that could be causing these black holes or neutron stars to get very close together. So there's all these very complicated story, and I've left out all the details about how all of these work because they're still being investigated, but all of these stories, each one of them could be right? It's not that it's one or the other. It could be a little bit of this, a little bit of this, a little bit of this. And all of these could be producing compact object mergers over cosmic time and eventually lead us to just measuring these noisy signals or these signals inside of very noisy data. And our problem is that we need to go back and try to do the inference on what all of these astrophysical processes were. And this is really, really difficult, okay? Why? Firstly, there's a very high dimensional source parameter space. So each one of those different channels or processes I showed you before, each one of those has multiple tunable parameters in it, on top of which I can have a mixture of all of those different processes with different fractions, which each is its own free parameter. There's a huge number of parameters I need to actually search when I want to do this inference. The data is noisy, as I said. So even when you do measure a merger, you can't measure exactly what the mass is, exactly what the spins are. You have these sometimes very large uncertainties on what those parameters are. To make things even worse, we have systematic uncertainties. So even if I could compute what, let's say, two stars in a binary will do over their lifetime, I might be able to compute what's happening, but I can't actually be sure that I put in all the right physics. And maybe I'm doing it in 1D, but maybe there's something in 3D that I can't simulate that, but I don't know if the 1D version is actually capturing all the physics properly. And then finally, it's not really good enough to show that any one of these channels can produce one of the mergers in our catalog. You need to really be able to explain everything, because I can always come along with my own favorite model of how one of the mergers is made, but someone else could have their own. And how do I actually, play these against each other, right? I can't just come and fit one thing, right? I've got to fit the whole population of sources that we've measured. So this all makes this a very difficult problem to actually do that inference on what's happening astrophysically to create these black hole and neutron star mergers. So let's try something a little bit simpler. Okay, what we're going to do is, instead of trying to, yes. It just symbolizes confusion. I see. Okay. Okay, thank you. Yeah, no, don't worry about the equations in here. It's just, this is what. Yeah, show anything with an equation to astrophysics, because they'll actually look at the equation. Okay. Yeah, so this is basically a very difficult problem, and it leaves people scratching their head. How can we actually do this inference problem? And so one of the ways we've tackled this is to say, well, maybe we can't do the inference on these detailed astrophysical processes, but maybe we can do some inference on some phenomenological models. So we can at least get some handle on what's going on. And then the people who are doing the hardcore detailed theory, they can try to explain some of these higher level phenomenological things we're finding in the population. So for example, I could just mandate that the black hole masses that we're detecting follow a broken power law distribution. And I could give the two breaks, the two parts of the power law different indices, and I can let those be free parameters, and I can fit that to the whole catalog of sources. So this is a very different approach from this kind of approach where I'm trying to actually simulate these black holes and neutron stars, possibly from zero-age main sequence. So there's sort of three classes of different models. So one are the very simple kinds of models. That's sort of like the one I just showed you in the last slide, like a broken power law to describe the population. The nice thing about these kinds of simple models is that you can ask very targeted questions. So I can ask a question like, is there a break in the distribution of black hole masses? Whoops. Is there even a break here? That's a question that I can ask using these sort of simple models. The simple models are also easy to write down. That's really nice. You can pass it over to your friend on a piece of paper. They're somewhat agnostic to astrophysical details, so you could call that a plus or a minus, depending on how you look at it, but that's just what you get. And the other downfall of these models occasionally is that you can miss important features, or because they're so simplified, they can actually give you biased estimates on certain things you're trying to measure. I also told you a little bit about the detailed astrophysical modeling, and that's nice because it gets our full understanding of how black holes and neutron stars interact. But it's hard to write down these models. You can't really hand it to someone else. You got to give them your whole monstrous code. They have many tunable parameters, and they may even still have systematic errors. I was saying you can't be sure that all the physics under the hood is actually correct. And there's one other class of models, which I haven't quite mentioned yet, which are these data-driven models. These are like the simple models, except they have a lot more flexibility, but they have very little astrophysics built in. You can kind of think of them as an analog to machine learning, right? They don't really know anything about what's actually going on. They just have lots of parameters and they latch onto data. The nice thing about these is you can find unexpected features in the population. And you can also corroborate the results you find with other approaches. And you can also get black box predictions you can hand to somebody else easily. So they don't have to know anything about the physics. You've just said, here's my empirical measurement. You hand it to someone else and they can do whatever with it they like. And the reason I'm illustrating all three of these is not to say that one is better than the other, but actually the exact opposite. There's a synergy among all of these things. Because this problem is so difficult, we need to be using all of these different approaches simultaneously to attack the problem from different sides and slowly narrow this like massively huge parameter space down to something that is more manageable, or at least something that we can say something interesting about astrophysically. Okay, so let's actually go on a little tour of using these different approaches to model the population of gravitational wave sources. So let's start with the simple models. I've just listed a few different papers here if anyone's interested in looking in some more detail at people who have done this type of thing. But I'm going to talk about a few specific works that I was involved with. So here was one. This was with some others in the room. One of the questions that we wanted to ask was, does the mass distribution of black holes change with redshift? Which is a sort of natural question to ask. The universe, the composition of the universe has changed over time. The number of stars, the mass of the stars, the metallicity, all of these things have changed over cosmic time. And you would think that that should leave some imprint in the black hole mass distribution over redshift. So we used a broken power law to describe the mass distribution. And so a broken power law has two indices, one for the lower masses, one for the higher masses, and then there's a breakpoint. And so all three of these are in principle tunable parameters. So the data can inform us on what these parameters are. And we also let this whole distribution move up and down. So we can increase the total rate of the signals or decrease it. So that's just an overall normalization of how many signals. So that's another thing we can use to fit the data. We'll let the breakpoint change as a function of redshift as well. So we'll let these two alpha-1 and alpha-2 parameters stay the same as a function of redshift, but we'll let the break and the height of this distribution change as a function of redshift, just to see, does it want to be different at different redshifts? So the first test we did was we said, let's just make this alpha-2 right here very steep. So essentially, this is going to just cut off right at m break, and we'll let m break move as a function of redshift. What do we find? So doing that, we found that at low redshifts, the mass distribution seemed to go out to about 40 solar masses and then cut off, while at higher redshifts, the mass distribution would have to go out to much higher masses. And so we thought, oh, look, we found evidence that the mass distribution is changing with redshift. That's awesome. That's a huge result. But that was a little bit too simplistic because we put in a hard cutoff here. So what if instead we allow that alpha2 to be any number it wants to be? We let the high tail of the mass distribution be a free parameter that can do whatever it wants. And in that case, you get a different result. And so here in orange, showing the low redshift mass distribution, and then in green, the high redshift mass distribution. And you can see that if I take this orange one and I just shift it upwards a little bit, then at least within the error bars, these two mass distributions have the same shape. They may have different normalizations, but the shape, there's no evidence that they are different, basically. So what we concluded was that the mass distribution, or the number of signals is probably increasing as a function of redshift, so that the actual density of signals is going up, but the mass distribution of them, there's no evidence right now that that's changing. So we couldn't tell yet if the mass distribution was actually changing with redshift, but this is something we're going to keep looking at as we get more sources. So each of these questions you can expect that this is something we're going to come back to in the next catalog of gravitational waves we're going to measure. All right, so that was one question that we answered, but that was a little while ago. Now something a little more recent. We were wondering, do black hole subpopulations of spin have different masses? So what do I mean by black hole subpopulations of spin? If we look at some of those detailed models that I was talking about and the different channels by which I can create black holes, I have one which is this dynamical channel with black holes potentially all in a dynamical environment where they can kind of get rearranged and brought close together. And in these kind of cases, you would expect the spins of the two black holes to be pointed in random orientations when they merge with respect to the orbital angular momentum. So the spin directions of the black holes could be anything. In an isolated binary channel where I just have two stars and through some interactions, they eventually become two black holes that can actually merge. In those cases, you'd expect the spins to be preferentially aligned with the orbital angular momentum. Okay, just because the stars are co-evolving together in one binary. So I kind of think about the dynamical channel as like a mosh pit. It's chaotic. And the isolated binary channel is like a tango or something. Okay. So we wanted to try to mandate that there's these two populations that are at play in the gravitational wave data, one with preferentially aligned spins, one with totally randomized spin directions, and check, do those two populations have different masses? All right, how do we do that? Well, we describe the spin orientations of the black hole, of each black hole, with respect to the orbital angular momentum of the system. So here I'm showing this L vector, that's the orbital angular momentum of this binary, and then here's the spin of just this black hole with respect to the L vector, and there's this theta angle, that's the angle between these two vectors. So if those spin directions were totally random of those black holes, then if I were to plot the distribution of the cosine of those angles, it would be flat because it's totally random spin orientations. If I'm in the isolated binary channel, then the spins should be preferentially aligned. So maybe it would look something like this. More support here at cosine theta of 1, and then around 0 at -1. Sorry, this should be 1 and -1, but so we gave each of these two populations its own mass ratio distribution and checked, are those two mass ratio distributions different? If they were, that should tell us something about what's happening astrophysically. So we tested this. So this was some work with Sierra fellow Vishal Vaibhav. And what Vishal did was he said that the mass ratio distribution, so Q is the mass ratio, let's let that distribution be a power law in the mass ratio and give it some flexible parameter beta. So if beta is very large, that means that the objects that are merging, they tend to have very similar masses. If beta is low or negative, then they're very dissimilar masses. So Vishal gave a different beta to both these black holes that should have isotropic spins, and then the ones that should have aligned spins. And he checked, what do the data support? So here on the x-axis, I'm showing the dynamical channel beta, and then the isolated channel beta on the y-axis. And then in blue here is the color represents the posterior support for a given combination of these two betas. And there seems to be some hints that maybe the dynamical channel beta is higher than the isolated channel beta, which is basically saying that in the dynamical channel, you want very similar masses of black holes to be merging, whereas in the isolated channel, where the two black holes have preferentially aligned spins, the masses are dissimilar. But this is just a hint. You'll see that there's this sort of equal beta line that could go right through here, and there is still some posterior support there. So, so there seems to be hints that maybe we can disentangle these two populations based on their mass, but we're not quite there yet. The data isn't giving us enough support for that. And Vishal went and overlaid a few population synthesis results. So these are using some of the detailed modeling. And he overlaid those onto this inference. And I don't want to go through too much into these models, but basically for globular clusters, so that's kind of going this direction, changing the globular cluster prescription. You always seem to prefer very similar masses, and that's because of mass segregation inside of globular clusters, for example. So at least in terms of the astrophysics, this seems to be kind of in the right direction, but we just need more data to actually empirically measure whether this is happening. So again, we can't quite tell what the answer to this question is, but we're getting closer. We're getting closer. We're actually, cutting out the distribution. So we're hopefully going to find something interesting soon.
What about
Correlation with totalness. We have looked at these. So people have looked at a bunch of these, and basically, I think in all the different ways you look at it, there's like hints, but it's not at the level. The one thing that has popped out is correlation with spin and redshift by Silvia Vescovino, who's actually going to join us at CITA next year. So, but yeah, some interesting work. Cool. So yeah, you can imagine you can play this game with all the parameters, right? And so people are doing that bit by bit. All right, so any questions before I move on? All right, so now I want to talk about some of the data-driven models. So these are the models with a lot of flexibility, but very little to no physics, okay? So one question we can ask is there some structure in the mass distribution of black holes that are merging in the universe? I showed you from Maya and my results that were a little bit above, as well as the results with Vishal, that we use some very simple like power laws and things to describe everything. But what if we do something a little more advanced? What if we took a power law for the mass distribution, and then we allow that power law to deviate in some sort of wiggly way, okay? And we'll make the wiggles parameterized by a spline function, and let that spline function change based on the data. So a spline basically has lots of little knots at different positions, and the knots have different heights. And once you prescribe those, the spline will do an interpolation in between each of these knots. So each of these knots becomes its own free parameter. So built in lots more parameters. They have nothing to do with the physics. They just allow this mass distribution to have lots more wiggles in it. Okay. So we can use this kind of model to check, is there some structure in the mass distribution of merging black holes? So Bruce Edelman, who I worked with at University of Oregon, he led some work where we used this model to reconstruct the mass distribution of black holes that were merging. And so this blue curve here and the blue bands show the uncertainty here. This shows the rate of mergers as a function of the primary mass, so the mass of the more massive object in each merger. And you can see it kind of falls off as you go to higher masses, but interestingly, there's a very nice peak here at about 35. And that peak was also found by this green model, which is a much simpler model that just has a power law and one Gaussian. And that Gaussian picks up this peak right here. Whereas our model, it has no Gaussians in it. It just allows all types of wiggles. And lo and behold, it reproduces this peak just as we would have expected from those simpler models. The other interesting thing is that it seems to be picking up some evidence for a peak at 10 solar masses that the simpler model just wasn't able to pick up. So the cool thing about these models is that, yes, they don't have any physics, but they can find things that you weren't expecting. Okay? So
could I just ask, I would have expected once you get to what appears to be a cutoff, that there would be an incredible uncertainty unless you put a prior on not to allow that uncertainty for even larger mass things. In particular, there's a mass range outside of the LIGO band that you can't get a handle on. So that's not really reflected in these error bars, is it?
yeah, not really. So for various technical reasons, many of the analyses we did with the second and third gravitational wave catalog, they didn't go beyond 100 solar masses for either of the objects, just because we couldn't have good sensitivity estimates out there. So all of our models had a cutoff that was fit to the data, and that cutoff does kind of find something around 80, 90 solar masses. But just like you're saying, there should be basically a tail out here of a lot of uncertainty if we give the models some more flexibility and actually estimate our sensitivity properly out there. And that's something that we are working on, and Reed is working on that within the collaboration. So
that's great. But from my perspective, because I love that mass range, that's an extremely important thing. And we would it'd be good to get the unpriored result, just to see what flexibility is there, given the inability of LIGO to go higher. That should be reflected. Anyway, I'm glad Reed's on the case.
Yeah. Basically, we have to inject lots more high mass signals so that we can actually figure out what their sensitivity is, and that enables you to do this. So yeah, that's in the works. Yeah.
Just really quick question: what's sigma naught in this model?
Okay, good. So those knots, their locations have to have some sort of prior. This is all Bayesian inference, so you need to have some sort of prior on them. And this is just saying what that prior was. But we changed that number a couple times just to see if it was changing the inference. You do always get the peaks, but you can make that number so large that it does eventually become, it sort of washes out what the data is telling you. But we did also, I think Bruce did actually do multiple runs with different numbers of knots and different priors and checked all of the information criteria to see which was the best fit and all of that. So I think this was the best fit model. Yeah. Okay, so conclusion, yes, there is structure in the BBH mass distribution. But to be fair, we weren't the people who realized this. This was realized before us, but we were happy to see our model was reproducing it without us putting it in. But you can try other types of very flexible models, and they give very similar results. So this is from the latest LIGO Virgo Cogra populations paper, where we try to fit the whole population of sources. And I know this is a very busy plot, so I'll just try to walk people through quickly. This blue line here is the most updated version of Bruce's fits with the latest data. And then this orange one here, this is a model made up of a lot of Gaussians and power loss. So it's also very flexible. And you can see both of these models pick up a peak right here at 35, a peak here at about 10, and then maybe something here at 20, but hard to say. I think since then people have looked into this, and it seems like what's going on here, there's nothing sort of statistically significant there, but there maybe is something interesting there we're going to keep watching as we get more detections. And then there's a histogram model where you have tons of histogram bins, and you let each of the bins be flexible and how many mergers are happening in that bin. And that one, again, also finds a similar, although with much bigger error bars, that the distribution does have a peak at around 35. And peak somewhere around here. So I think some people might look at this and say, wow, there's lots of different inferences you're making. That doesn't seem good. But from my perspective, we don't actually know what's happening out there astrophysically, right? This is all empirical modeling. So we have to use lots of different approaches and lots of different phenomenological modeling just to make sure we're not fooling ourselves. So I think this has been a really cool development, is throwing more of these kind of models at the data. Okay, I'm going to skip through a couple more slides because I want to get to some of the detailed modeling before we wrap up here. So in these detailed models, people are actually simulating, for example, pairs of stars from ZAMs through till when they become two compact objects and merge. So these models can be very expensive to run, but I'm going to highlight just one of the possible channels. I talked about this isolated binary channel. I'll just show again another little cartoon. We have the two stars to begin with. I told you that simple story of just turning them into black holes and merging them, it doesn't work because the stars will get too close. So what you can do is instead you can invoke some sort of mass transfer processes. So maybe there's some mass transfer from the star onto one of the other bodies once it turns into a black hole, or maybe it's some sort of so this is called stable mass transfer, where it's sort of a stable process, or it could be that the mass transfer starts happening onto the black hole so fast that the black hole can't actually eat up that mass fast enough, and it all just kind of starts turning into this massive envelope around the star and the black hole. And one of these two processes, or both of them, could be at play during the evolution of the binary. And then that would eventually bring the two black holes close enough that they could merge. And which of these exact stories is still under hot debate. Okay, but this is sort of set of techniques people are looking at, or set of channels people are looking at. Okay, so one of the cool things about these detailed models of these, say, these isolated binaries is that you can actually compare between totally different data sets because you're actually simulating the real physics. You're not doing some phenomenological modeling. So we can actually compare things like black holes that we're finding from gravitational waves to those we're finding, say, in high mass X-ray binaries. So let's go back to this chart I showed at the beginning. You'll notice that the black hole masses that we've detected in LIGO, Virgo, and Kagra in blue, these tend to be higher black hole masses than those found electromagnetically. So those are the ones that you would find in high mass X-ray binaries, for example. So this is possibly puzzling. Maybe it's expected. I think this was an open question. And so one of our students at Northwestern, Camille Leotine, she used the code COSMIC, which, yes.
To go back to
Mass distribution you showed earlier. Every version, I don't think it matters. And then you.
All right, this one.
Yes. Okay. So you say up to about 20 solar masses. Okay, I'm going to have n black holes equal to the number that have been discovered in the galaxy. And then I ask, given that mass distribution, how many do I expect to have formed above 20 solar masses? How many is it?
I'm not sure I understood the question. So you're asking. Yes. Oh, okay. So you're saying.
So given that mass,
Hmm.
given the number of black holes you've seen 20 or less in the galaxy,
How many does that black hole mass distribution?
Yes.
Of
Okay, so Maya has actually looked into this, and I believe that there is an inconsistency in the mass distribution when you actually do the fitting of both the populations. Is that?
Yeah, there is no inconsistency if you're looking at high mass X-ray binaries. If you're looking at the black holes in high mass X-ray binaries, there are 3 that have robust mass measurements, and those are perfectly consistent with coming from this mass distribution. If you include low mass X-ray binaries, then those black hole masses are too low. and they're not consistent with just being drawn from this primary mass distribution. There are like 20 something of those, but they have very, very low mass companions. So
Right. So
if you take into account like a 2D mass distribution,
that's what the merging channel.
yeah, I mean, I think that's what Zoheyr is going to talk about next.
Okay, sorry.
Yeah, so sorry about missing. So yes, in the high mass X-ray binaries, there is at least consistency with the few that have been found, but the low mass X-ray binaries, no, but you can't tell, is that just because we've done some weird selection of which objects even count, you know? So it's hard to do the comparison in a very fair way. And that's sort of what our student Camille was attempting to do in this project. So she used this code Cosmic to simulate lots of binary star systems, all the way through an HMXB phase and possibly all the way till they merge as two black holes. So I'm going to show you a plot here. I'm not going to tell you what's on it yet, but x-axis is the mass of the black holes. The y-axis is the mass of the donor when it's a high mass X-ray binary. And you're going to see two populations show up here. So here are the high mass X-ray binaries in orange. And then some subset of these go on to be merging black holes. And those are shown in these black contours. And the inside of the contour is 50% credible region. The outside contour is 90%. So you can see just by looking at what things turn into high mass X-ray binaries that and those that turn into merging black holes, they're slightly different mass distributions. But you can overlay on top of that the selection effects of the instruments. And that makes these distributions become even more disparate, because in LIGO and other instruments like that, we're more sensitive to more massive mergers. So basically what Camille's work was finding is that if you do see some slight discrepancy in these masses between high mass X-ray binaries and black hole and gravitational wave black holes, it's not anything funky, potentially. It could just be that there's the selection effects both through the evolution as well as through the detector selection effects and the survey selection effects. Okay, how much time do I have, Phil?
3 minutes.
Okay, perfect. 3 minutes is all I need. All right, great. So I think I mostly said the main conclusions of that. I just want to get to one last piece here, which is like sort of the next frontier of the detailed modeling. And that is a code called Poseidon. So this is being co-developed at Northwestern. I'm actually not a developer, but a bunch of my students are. So I have to make sure I show their work. So I know it's a really complicated diagram, but that's because what's happening under the hood of this code Poseidon is in fact quite complicated. It starts by creating ZAMS binaries and evolving them through a bunch of different sequences all the way until they reach some sort of end state like double compact objects, stellar mergers, disrupted binaries. And the thing that Poseidon has put in that other binary population synthesis codes have not quite gotten up to this level is essentially replacing a lot of the very complicated physics parts with actual MESA simulations. So running literally thousands of MESA simulations of binaries with different parameters and using these massive grids of simulations to then do interpolations at each of these particularly troublesome steps of the evolution, where the stars are evolving internally on a similar timescale to which they might be transferring mass between each other. So that's sort of handled much more self-consistently than before. And I just want to give a couple shout outs to a couple of students. One is Kyle Rocha, who's going to be here next week. So you should definitely ask him more about this. I'm not going to say anything more since he's going to be here, but he's been working a lot on Poseidon. He's one of the big developers, so definitely ask him about it. And then finally, I just want to get back to this question about whether the masses are consistent. Another thing that Maya looked at was not just the masses, but the spins. Okay, and it was the spin distribution that definitely seemed to be saying there was some sort of inconsistency. In the orange, we've got the binary black holes from LIGO Virgo, and then in the purple and blue are the LMXBs and HMXBs, and these are CDF. So you can see these LMXB and HMXB spins are much higher than the ones you're seeing through merging black holes. And so our student Monica worked with me and Maya and others to use a Poseidon-like infrastructure, so lots of MESA simulations to try to see do any of these high spin HMXBs become high spin merging binary black holes. And I'm not going to go through the details since we don't have time, but the main conclusion was that very few of these HMXBs that we think will have high spin end up being merging black holes. And the flip side of the coin is that only 20% of the mergers that we're seeing as black holes in LIGO and Virgo came from this channel where we think that you get high spin in the HMXB. So I'm just going to finish things off here. I know we're out of time, so you can ask me questions after, but I've talked about a few different approaches to modeling these populations of gravitational wave sources, and I hope I've convinced you that you have to kind of come at this at lots of different angles because the problem is very difficult. And ultimately, I think the big thing is that this is a really big team effort. We need people both doing the detailed nitty-gritty modeling of stars, dynamics. We need people on the exact opposite end of the spectrum doing the statistics, machine learning. We need detector experts involved as well to understand the sensitivities of all these different instruments. So all of this has to come together for us to really figure out where all these black holes and neutron stars are coming from such that they can merge in the age of the universe. So thank you very much. I'll take some questions.
Thanks a lot. So here, let's open it up for questions. Are there any in the room?
Can you remind me what's the physical reason for the peak at 10 solar mass and at about 35 solar mass?
Great question. We don't know.
Oh,
I think some people would say that they would know, right? But I think that's the point of these very flexible models, is that we can look for these features, and then all the people who are doing the nitty-gritty theory, like you, can say, huh, how can I get that from my detailed models, and what might be an explanation for that? But as far as I know, these are big open questions that people are still grappling with.
thanks.
Thanks. First of all, great talk. Second of all, might be kind of a pretty simple question, but how important is the mass of kind of the merging objects in detecting a gravitational wave, I guess, detection? I only ask because I would assume a larger mass means like it'd be easier to make a detection, which is why we don't see, say, white dwarf mergers. But then why don't we see stuff like intermediate mass black hole mergers? Why do we need stuff like LISA and Einstein telescope to be able to detect those?
Good question. So you're right that as you make the mass of the mergers larger, the amplitude of the gravitational wave goes up. And so nominally, you would be able to be more sensitive to those. And that is actually the case as you go up in mass from a few solar masses to tens of solar masses. And that's why if you look at the actual mass distributions that we have inferred of the underlying population, right, they're very high at low masses, but then they fall off. But if you actually look at the detected ones, they tend to live all around 30-ish solar masses. And that's just because of the selection effect of we're better at detecting things that are higher mass. Now, let's say we go even higher mass than 100 solar masses. Then you start hitting other problems. The signals become much lower frequency. And as a result, the number of cycles that you can actually detect in the detector becomes lower. So basically all you're seeing is like 1 or 2 wiggles, and that's it. And so they become harder to detect, or at least harder to distinguish from noise in the detector. So if you look at the sensitivity to different masses, it goes up and then eventually starts to fall off again. And Maya actually has a paper that shows this nice graph like that.
So like a longer baseline, like in, say, the Einstein telescope would fix that? We'd be able to detect these lower frequencies, or what? How would we ever be able to detect these lower frequencies?
Well, so the longer baseline would be part of it, but I think that the biggest problem is going to be some of the other noise sources that are causing, so like the seismic noise and all of that. Like if those are not mitigated properly, then you can still have low frequency issues. And I think that's part of what we've been kind of pushing up against in LIGO now, is just trying to beat down these weird little noise sources so we can actually get the sensitivity.
Thank you.
In response, yeah, I got one. So just a quick point on this, like there's some really There's some really one of the if you could shield your detector from everything in the world, all noise sources, the one thing you don't want to shield it from is gravity. But as a seismic wave comes through, passes through your detector, it may shake and rattle stuff, but it will also be associated with compression and rarefaction of the stone. And so you get different gravity density gradients. And this happens with clouds and other density gradients. And you do not want to shield your detector from that change in gravity. And those tend to happen at very low frequencies. And therefore, there could just be on Earth insurmountable noise sources down there. No, that's one of the reasons why to go into space, you can get longer arms and you don't have to worry about the Earth shaking. Yeah.
Thank you. I think there were a couple of things up back there.
Great, thank you so much. So in your plot of Poseidon's flowchart there, you had some modeling for detached binaries. Does that include tidal effects? And if so, which kind of effects are you including? Which seem to be important?
So I'm trying to remember what happens in the detached binary evolution. I'm pretty sure that the tidal effects are accounted for during that step. Let me think about that. I think that they are probably accounted for in the binary evolution in terms of the orbital separation, but I think the internal structure of the star is probably not changed self-consistently during that phase, because I think single star models are used when it's a totally detached binary. Yeah. So there's lots of places to add more to this. Yeah. Absolutely.
Okay, were there other questions?
Yeah, I have one, if that's okay. Can you go forward to, I think it was one of the last ones, it was the spin distribution, which I found tremendously, of course, we have our expert at CITA on this, but it's incredibly stark. And so it suggests that everybody should be on this game and try and understand it. So what is the understanding of why this is so different? What is selecting against these higher spin entities that are in the X-ray binaries that they're not merging? Is it because they've spun up or something?
Yeah, so I'm not exactly sure why those specific binaries don't end up merging, but basically when you look at the things that at least you would think would get spun up in case A mass transfer, which doesn't necessarily need to be the way that these black holes get their spin. There could be other things, right? This was just one thing we considered in I think this was actually in this work. In that case, it just naturally comes out that the things that do get spun up don't also tend to be the things that turn into binary black holes. And so I didn't really have a chance to talk about these plots, but basically you can see here in black, these are the things that get turned into binary black holes that merge in a Hubble time. And this is all the things that are case A, go through case A mass transfer in these dots. And the intersection between these is just very small.
So could it be that binaries, because that's where it's coming from, that they're sort of an older class, and so the concept of all of the accretion is not so relevant?
I'm sorry, say that one more time.
Well, I'm thinking that there is a population of binary black holes that might have formed at high redshift, and then they just slowly spiral in together. But as they spiral in together, presumably they don't have that much gas to spin them up and accrete. I mean, of course, I'm just throwing out something because it's so intriguing. And I expect that the experts would know a lot better of whether or not this is a feasible issue. That is to say, birth date of the binary systems would be of relevance here.
Just one thing about that, Dick. So the spin for high mass X-ray binaries, it's really hard to get that from accretion onto the black hole because the systems don't live as long. And so there's not enough time to get enough accretion to actually spin up that black hole. So we think that those black holes are born with those spins. In the low mass X-ray binary, because those are accreting stably and we don't know what masses those black holes were born at, they could have been born at lower masses and just accreted a lot of mass to explain their spins. But they're also, the low mass X-ray binary spin distribution is consistent with the high mass X-ray binary one. So it might be like there may be an Occam's razor argument there why you don't want to use accretion for one of them.
But Dick, I mean, remember that to get an X-ray binary, you need to have the two stars close enough to transfer mass.
Yeah.
So there's a selection against wider binaries, which would still experience a common envelope in the late evolution of the second star. And then, according to Maya's et al. Models, would have smaller angular momentum in their cores because the star was more extended when the interaction finally took place. But can I just ask one final question of Claire and Maya and the speaker, which is this is intriguing result that there's consistency more or less, with, as I understand it, with the mass distributions with high mass X-ray binaries, but not with low mass X-ray binaries. So the question maybe first for Claire is, okay, you put the full astrophysical complement of black holes into a star cluster, including the high mass and low mass systems, but let them all mush up and exchange companions and so on. But then there'll be stronger mass segregation. So the question is, if given, taking into account the stronger mass segregation of the higher mass black holes to the center of the cluster, how well represented is the merger, mass distribution in the dynamical channel, a representation? How good is it a representation of the initial mass distribution that you're putting in?
That is a great question.
So in other words, you put all these stars in, because the argument was, well, in the low mass case, the second star can't form a black hole. So you're never going to form if it's just the isolated binary channel, you're never going to form a merger, double black hole merger. But, is it really inconsistent with the dynamic channel, taking into account all these additional dynamic effects?
Models, a lot of those like really low mass black holes that we see in the low mass X-ray binaries too, they get kicked out of the cluster at birth. But I think that might be something wrong with the models, because we do see like a 5 solar mass black hole in a globular cluster.
The higher mass one take out first, and what's left are the 5 solar mass ones.
Really?
Because the higher mass ones will be the first to form and the first to mass segregate, and then they will have the most dynamical encounters early on. And then if they're not massive enough, by massive enough, I mean to 1,000 solar mass, like intermediate mass black holes, they will be kicked out at some point during dynamical interaction.
Well, it sounds like you guys should get together and, reach an agreement on this, because
Yeah, I mean, that's the 2 kinds of effects, like the natal head.
Yeah.
Supernova, don't understand.
So maybe I'll suggest that we continue this discussion in the lounge. Thank you very much, Zoheyr. Let's thank him.